What you're about to see is forging in its purest, most impressive form, the kind of work that connects us directly to centuries of metallurgical tradition, now executed with remarkable modern precision at ASO Forge. The process begins with raw steel billets, heated in enormous furnaces to temperatures around 200 degrees Fahrenheit. At this temperature, the steel glows brilliant orange-yellow, hot enough to become plastic and workable, but not so hot that it melts. Temperature control is absolutely critical. 50 degrees can make the difference between perfect grain structure and a rejected piece. Now watch as that glowing billet moves to the forging press. What you're witnessing is open die forging, where massive hydraulic hammers weighing dozens of tons strike the steel repeatedly. Each blow isn't just shaping the metal, it's actually refining the internal grain structure, aligning the crystalline structure for maximum strength. This is fundamentally different from casting or machining. Forging creates parts with superior mechanical properties. See how the operator rotates the billet between strikes? That's skilled craftsmanship right there, ensuring even deformation throughout the piece. The steel gets progressively longer and thinner with each pass, the diameter reducing while the length extends. Between forging operations, the steel may return to the furnace for reheating, maintaining that optimal working temperature. The color tells experienced operators everything. When it fades from yellow to red, it's time for another heat cycle. After forging comes controlled cooling, often following specific temperature curves to achieve desired hardness and toughness. Then machining, heat treatment, and rigorous testing. What emerges is specialty steel bar stock with guaranteed properties. There's something deeply satisfying about watching a single, perfectly engineered tool do the work of three. And that's exactly what the Walter Tools M4000 indexable insert milling cutter brings to the table, or rather to the spindle. The M4000 is what machinists call a universal face mill, and that word doesn't do it justice. This cutter is engineered to handle face milling, shoulder milling, and chamfering, all in one pass with one tool setup. For any shop running high-volume production, that means less downtime, fewer tool changes, and more parts out the door. Let's talk about what makes this cutter tick. The M4000 uses a tangential insert clamping system, meaning the cutting inserts are locked in from the side rather than the top. This might sound like a minor detail, but it's a game changer. Tangential clamping creates a much larger support surface behind the insert, which dramatically reduces vibration and flexing during heavy cuts. You get a cleaner surface finish and a tool that simply lasts longer. The inserts themselves are single-sided, precision ground, and made from carbide grades optimized for everything from aluminum to hardened steel. Each insert features 4 usable cutting edges. You flip it, index it, and keep cutting. No waste, maximum economy. Now watch as the M4000 engages the workpiece. Notice how the cutter glides across the surface. That's the result of a positive cutting geometry that reduces cutting forces. Less force means less heat, and less heat means your part stays dimensionally accurate. In aerospace and automotive applications, we're talking tolerances tighter than a human hair. The chamfering capability is where things get really clever. The M4000's insert geometry naturally creates a clean 45-degree chamfer on the shoulder edge. As it mills, no second operation needed. One pass, 3 results. Flat face, square shoulder, clean chamfer. That's engineering working exactly the way it should. For shops dealing with tough, long chipping materials like stainless steel or titanium, Walter engineers the M4000 with optimized chip gullets, the pockets between inserts, to evacuate chips quickly and prevent recutting. Coolant through the spindle keeps everything crisp. Founded in 1902 in the Swedish village of Gränsfors, this company has been hand-forging axes the same way for well over a century. And watching their craftsmen work, you start to understand why the world's finest woodsmen, foresters, and outdoorsmen have sworn by this name for generations. Every axe starts with steel, specifically a high-grade Swedish steel selected for its toughness and edge retention. The raw steel arrives as rod stock, and the first step is cutting it to a precise billet weight. Every gram matters, because every gram will become part of the finished axe head. Next comes the forge. The billet is loaded into a gas-fired furnace and heated to around 200 degrees Fahrenheit, a brilliant, almost white-orange glow that tells the smith the steel is ready. At this temperature, the steel is plastic, almost like thick clay. It wants to move. The smith moves it to the power hammer, a massive, rhythmically pounding machine that delivers controlled, repeatable blows. But don't mistake this for automation. The craftsman at Gränsfors is guiding every strike, rotating and positioning the billet with practiced hands. He's reading the steel, watching how it flows, feeling the resistance through his tongs. It takes years to develop this intuition. The axe head takes shape through multiple heating and hammering cycles. The pole, the flat back of the head, is formed first for structural integrity. Then the bit, the cutting edge, is drawn out. The eye, the hole where the handle fits, is pierced using a drift punch driven through the hot steel. Each operation requires the steel to be reheated to maintain workability. After forging, the head goes through heat treatment, normalized, hardened in oil quench, then tempered to reduce brittleness. This precise thermal cycling gives the Gränsfors axe its legendary balance of hardness and toughness, an edge that holds but won't shatter on a cold morning. Then comes hand grinding, where craftsmen shape the bevels and cutting edge with rotating grinding wheels, checking the geometry by eye and touch. Finally, the handle, American hickory, straight-grained and resilient, is fitted by hand, the fit tested for tightness and alignment. Each completed axe is inspected and stamped with the individual craftsman's initials. That's accountability you can hold in your hands. That's a Gränsfors Bruk axe. If you've ever watched a bandsaw slice through a thick steel bar like it was butter, you've witnessed bimetal blade technology at work. And the story behind how these blades are made is every bit as impressive as what they can do. A bimetal bandsaw blade is exactly what its name suggests. Two different metals, permanently joined, each doing a job the others simply can't. The blade body, the long, flexible strip that loops around the saw's wheels, is made from spring steel. This is a carefully alloyed steel with excellent fatigue resistance. It bends thousands of times per minute as it travels around the saw's wheels without cracking. Flexibility and toughness are its superpowers. The teeth are a completely different story. They're made from high-speed steel HSS, a tool steel packed with tungsten, molybdenum, and cobalt. HSS holds a cutting edge at temperatures that would turn ordinary steel soft. When you're cutting through hardened steel or stainless at high feed rates, the blade teeth can reach extreme heat. HSS laughs at that heat and keeps cutting. The manufacturing process begins with an electron beam welding machine, a remarkable piece of equipment that fuses the HSS wire to the edge of the spring steel strip using a focused beam of electrons in a vacuum environment. The weld zone is incredibly narrow and precise, just a few thousandths of an inch. The bond is metallurgically perfect. After welding, the composite strip goes through tooth forming. The teeth are milled or ground to precise geometry. Then heat treatment hardens and tempers the HSS cutting tips to optimal hardness. Set and sharpening finish the process. Bending a metal tube sounds simple. Until you try it. Apply too much force and the tube collapses. Bend too fast and the outer wall cracks. Get the radius wrong by a fraction of an inch, and the part is scrap. That's exactly why Kism CNC pipe bending machines exist, to take the guesswork out of one of metalworking's trickiest operations. The Kism bender uses a mandrel bending process. As the tube is bent around a precision die, a mandrel, a shaped steel plug on a flexible rod, sits inside the tube at the exact point of the bend. It supports the tube wall from the inside, preventing collapse and wrinkling. A pressure die pushes from the outside. A wiper die prevents material from buckling at the inner radius. CNC control manages every parameter, bend angle, rotation, and feed, all programmed to fractions of a degree. Complex multi-plane bends that once required hours of manual setup now run in minutes, with every part identical to the last. Aerospace hydraulic lines, automotive exhaust systems, architectural railings, Kism machines bend them all with the same quiet, confident precision. Welcome to the world of heavy-duty precision machining. The face lathe, sometimes called the vertical lathe or VTL depending on orientation, is the workhorse of heavy industry. Rotor shafts for power plant turbines, axles for railway locomotives, propeller shafts for ocean-going vessels. The machine you're watching is a horizontal face lathe engineered specifically for extreme loads. The bed is cast from high-grade gray iron, stress-relieved through a weeks-long thermal cycling process to eliminate internal stresses that could cause the machine to drift out of alignment over time. The spindle bearings are massive hydrostatic units. The spindle literally floats on a pressurized film of oil, eliminating metal-to-metal contact and with it, wear and vibration. Loading a 120-ton workpiece is itself a carefully choreographed operation. Overhead cranes, precision alignment tools, and experienced riggers work together to set the shaft on the lathe's steady rests, support stands that prevent the massive workpiece from deflecting under its own weight during machining. Even a few thousandths of an inch of deflection would ruin the part. With the workpiece secured, setup begins. The operator mounts a heavy-duty carbide or ceramic turning insert, tools engineered to withstand cutting forces measured in thousands of pounds. Depth of cut, feed rate, and spindle speed are programmed into the CNC controller with the care of a surgeon planning an operation. As the spindle turns, watch the cutting tool move steadily across the face of the shaft. The surface behind it is mirror smooth, a finish that will allow precision bearings to seat with zero play. The chips coming off are thick, curling strips of steel, glowing with heat. Each pass removes exactly the programmed amount of material,